Hi, this is part 3 of the 2018 June Maths Higher Paper 1. Questions 1 to 13 are on 2 other videos. Okay, so this is question 14, hopefully to the end in 15 minutes. Okay, our first question here is an indices question. We've got 9 to the power 3 over 2. So the 2 on the bottom is telling us the root we need to do, so it's a square root. So our first job is to square root 9. Which is 3. Then we've got a 3 on the top, our numerator is 3. So then we've got to cube our answer, that means. So now we have to do 3 cubed. 3 cubed is 27. 27 is in our list there. Okay. 10,000 to the power of minus a quarter. Okay, so if you look at your denominator, that tells you your root. So the root type this time is the fourth root, so not one you do often. So the fourth root of 10,000 something times something times something times something is 10,000 is 10. Okay, then we've got a minus there. Okay, a minus and a power means reciprocal 1 over. So then it's 1 over 10 and our solution is there. Okay, question 15. Okay, question 15 next. So this is a recurring decimals question. You need to start by writing the decimal out sort of in its long form, so that'll be 0.2454545. Only the 4 and the 5 are recurring. Okay, and then the aim is then to keep going until you get two numbers which are matching after the decimal point. So 10x times everything by 10 would be 2.4545, so they don't match. And 100x would be 24.5454, so none of those match. And then 1000x is 245.4545, and we've seen that before. So that bit there after the decimal point matches up with that row there. Once you've got two matching rows, then you need to take the two rows away from each other. So it's 1000x take away 10x, so on the left we've got 990x, on the right these cancel out, leaving us with 245 take away 2, which is 243. And then the last job then is to turn it back into a fraction with x on its own, so x equals 243 over 990, no need to simplify. Okay. Then moving our way down to the third question, so we've got some brackets to expand. So this is going to be FOIL. Okay, so we've got 8 times 5, which is 40. Then we've got 8 times root 7, so that's going to be just 8 root 7. Then we've got 5 lots of minus 3 root 7, so that's minus 15 root 7. And then last of all, we've got to multiply 3 root 7 by another root 7. So 3 root 7 times another root 7. Remember that these will just become 7. Okay, so that becomes 3 times 7, which is 21. We've got a plus there and a minus there, so minus 21. All we've got to do then is tidy it up. So our rational parts, the 40 take away 21, that gives us 19. And then the irrational parts, we've got plus 8 root 7, but we're taking away 15 root 7. 8 take away 15 is minus 7, so minus 7 root 7. And sometimes you're asked to state whether that's rational or irrational, and because we've still got this root part hanging around, that's irrational. Okay, next question. So this is actually an indices question. Okay, this is an unusual one actually. And we've got to draw a graph of 2 to the power of x. So y equals 2 to the power of x, and x is going to take values between minus 2 and 2. And you've really got to know your indices rules here. Okay, so in our first one, we've got to do 2 to the power minus 2. So that's treated like 2 squared to begin with, so that's 4. But the minus means 1 over, so 1 over 4. Okay, For the next one then, we've got 2 to the power of minus 1. If the minus wasn't there, 2 to the power of 1 is 2. And then we've got the minus, so it's 1 over, so 1 over 2. So far we've got a quarter and a half. For the next one, we've got 2 to the power 0. Anything to the power 0 is 1. Here we've got 2 to the power of 1, so that just stays the same. That's a 2. And then the very last box, we've got 2 to the power of 2, which is 4. We had that earlier, but we had a minus, so we made it 1 over. And then all you've got to do then is plot it down here. So our y values, our maximum is 4. So if we went 1, 2, 3, 4, and our x values go from minus 2 to 2. So if we go minus 1, minus 2, and then 1 and 2, and then it's just reading off. So we've got a quarter, a half, 1, 2, 4. So a quarter would be there, a half, 1, 2, and 4, which makes an exponential curve. Join it all up, and we get something like that. You've got to try to be accurate on this because of the next question. It says, use your graph to find the value of 2 to the power of 1.4. So that's 1.4 on the x-axis first of all. Remember, it was 2 to the power of x. So when x is 1.4, which is there, we need to go up and across. So up and then across. And I've got 2.5 or 2.4. Okay. So let's put that in. So 2.5. And then it says use your graph to solve 2 to the power of x equals 1.4. So this time it's the y that's 1.4 we're looking at. So we're going to come across from 1.4 this time and down. So 1.4 is there. Okay. And then down. And that comes out at about 0.4. Possibly you might get 0.5. Depends on how well you drew your curve. So 2.5 for part B and 0.5 for part C. Okay. Question 17. This is a probability question. It's without replacement. It's right at the back. Okay, this is a star work now. Children's party. The children play a number of games. They get a prize. The prize is not returned to the box. At the start of the party, there's 12 prizes available. 1 book, 3 keyrings, 8 pencils. Find the probability that the winners of the first 2 games choose the same type of prize. Well, straight away you've got to spot that they can't both win a book because there's only 1 book. So our options are, we could get a keyring for the first prize winner and another keyring for the second prize winner. Okay. And there's times. So when the first child goes up, they've got a 3 in 12 chance of winning a keyring. And then after it's been won, the next child has got a 2 in 11 chance of winning. So that gives us 6 out of 132. The other way they could both get the same prize is they could both win a pencil. So we've got the probability of the first child winning a pencil multiplied by the probability the second child wins a pencil also. So that's 8 out of 12 chance of the first child winning a pencil. And if they've already won a pencil, there's only 7 left in there out of 11. So that gives us 56 out of 132. It doesn't matter what prize they get, so we can use the OR rule. So we need to add these up because of the OR rule. That gives us 62 out of 132 is the total probability of the first 2 people winning the same prize. Okay, part B. After the winners of the first 3 games, so 3 fractions this time, have chosen their prizes, find the probability that the ticket for the book is still in the box. Okay, you've got to think a bit outside the box on this one. If the book is still in the box, it's because it hasn't been won. So we're not interested in what the children did win, it's more about what they didn't win. None of the first 3 children won the book. Okay, So what we're looking for is the probability that the first child does not win the book. Okay. Multiplied, because it's AND rule again, that the second child does not win the book. And then same thing again, times that by the probability that the third prize winner also does not win the book. That's the only way the book can be left in there. So if we go back to our numbers, when the first child goes up to play, there's 12 prizes in the box and 11 of them are not the book. When the second child goes up to play, there's 11 prizes in the box and 10 of them are not the book. And when the last child goes up to play, the third child, there's 10 prizes in the box and 9 of them